Okay, let's continue. Now one more piece. Higher order partial derivatives. So consider a function, say, of two variables, f of x, y. We can, suppose that this is a function sufficiently regular so that I should not care about existence of derivatives. It's differentiable and even more. So we can find fx equals df dx, fy equal df dy. Now these are also functions of two variables, and we can also differentiate them. Yeah. So we can form, but now we can form four different derivatives. F xx equals dfx dx. Fyx equals dfx dy. So I take the function fy, fx differentiated with respect to y. fxy equals dfy dx. fyy equals dfy dy. So we can form four different functions by differentiating. Now consider example. F of xy equals, say, sine of xy square. We can take arbitrary function. Let's take this. So fx equals cosine of xy square times differentiate this y square. So y is a constant when we differentiate with respect to x. Fy equals cosine xy square times 2xy. Yeah, x times 2y. Fxx. So we differentiate fx with respect to x. So first we differentiate this minus sine x y square times y square times y square. Yes, equals minus sine xy square times y4. Fyx. So we have to take fx differentiate with respect to y equals minus sine. One moment. Let's be accurate. So we have to differentiate the product. It is fxx equals minus sine xy square times y square times again y to the 4. Now the second term is 0 because derivative of y squared with respect to x is 0. F yx. We have to take fx, differentiate with respect to y. So it is minus sine xy square. So we differentiate with respect to y, so here times 2xy times y square. Now we have to add cosine xy square times, now we differentiate with respect to y, it is 2y. F xy. This time we take fy, differentiate with respect to x, equals minus sine of xy square times y square times 2xy. Now we have to differentiate this plus cosine xy square times this time 2y. And the last is fyy. So we have to take fy, differentiate with respect to y. So it is minus sine xy square times 2xy times y4 times times 2xy times 2xy, yes, plus we differentiate the product, cosine xy square times 2x. Yes, I hope I made no mistake. So what is interesting in this jiggling the formulas? Let's see, fyx minus sine times this and fxy, you see that they are equal. Yeah? Fyx equals fxy. I think this circumstance was found soon after people invented the machinery of differentiation. It could not go without notice. So we can try, and definitely these early mathematicians of 17th century tried different combinations of functions. They differentiate in this order and other order, and every time found that results are equal. Yeah. So it was led them to the conjecture that it is universally true. And so it was formulated in four-link theorem. No, theorem after Clairaut. Suppose fx, fy, fxy fyx exist and are continuous, then fxy identical fyx. No, the exist means the corresponding functions are differentiable, continuous and differentiable functions. The functions which are defined by formulas, algebraic or trigonometric or exponential and so on, are always differentiable, continuous, outside of some singular points where they are discontinuous or go to plus minus infinity, something like this. But in most points it is true. And in these points we have this formulation. No, in fact, I don't believe that Clairaut really proved this theorem because in other books it is named Schwarz theorem. Schwarz was a German mathematician about 100 years later than Clairaut. And it is more likely because in fact it is not very difficult, but belongs to analysis, and it is really unlikely that Clairaut, who lived in mid-18th century and was in fact astronomer and not mathematician, that he really proved this theorem. No, Clairaut, Schwarz also, Hermann Amando Schwarz, he did it very clean. I just want to show you the idea how we can think about this theorem. So it is idea of the proof. Consider the point x, y, yes, and then the point x plus dx. Dx is very small quantity, y, the point x, y plus dy, and the point x plus dx, y plus dy. And let us denote these points, say, A, B, C, and D. So we have these 4 points. And let us write f of B minus f of A is approximately equal fx at the point A times dx. So f of B approximately equal f of A plus fx at the point A dx. F of C approximately equal f of D plus fx of C dx. F of D approximately equal f of A plus fy of A dy. F of C approximately equal f of B plus fy of B dy. Now consider f A f of D minus f f of C minus f of D, C minus D, minus f of B minus f of A. Approximately equal, this is equal f of C minus f of D, fx of C dx minus fx of A dx equals fx of C minus fx of A d. dx. Now what is fx of D minus fx at A? Again, I write approximately fx of D minus fx of A. It is fy approximately equal of A dy, it is this, dx. Yeah? On the other hand, if you compare this, f of C minus f of B minus f of D minus f of A equals, so f of C minus f of B, it is approximately equal fy of B dy minus fy of A dy, which is equal fy of B minus fy of A dy. And this is approximately equal fy of B minus fy of A. Yes, it is approximately equal fxy of A dx dy. So I took this. No, you can see it this longer than I tell you about this. And what is the most important, that both this and this equal, this is, so f x y, yx of a dy dx is approximately equal, what is written here, f of a minus f of b minus f of d plus f of c. So you take this with plus and this with minus. B and D with minus. And f xy of A from this is approximately, dx dy approximately equal, what is written here, f of A minus f of D minus f of B plus f of C. We see that left hand side here fyx, here fxy, and to the right we have the same terms in a little different order. So from here you see that fxy of A approximately equal to fyx of A. Now what I can say, here we used several times this sign approximately equal, and we have to explain it in more exact terms, which Clairaut really did not do. I don't believe that he, not only that he could do, but that he understood that it should be done. For him it was all clear. And Schwarz really did. And this is more or less the idea of the proof. Now if you want to find, say, this fxy numerically, if you have a function of two variables and you have evaluate its second derivative, second mixed derivative, fxy, fyx are called mixed derivative. It is done even today. We take such 4 points forming a small rectangle and find this sum, divide by dx dy, and have approximate value of second mixed derivative. Similar things are done in 3 dimensions. So we have a function f x, y, z. So we define derivatives first order. Fx is df dx, fy df dy, fz df dz, yes? And then we define the second derivative. fxx equals dfx dx, fyx equals dfy fx dy, fzx dfx dz, no, and so on. The last will be fzz equals dfz dz. So this is second, so in three variables we have 9 different derivatives, but the same as in the plane, some of them are equal, namely the mixed derivatives are equal. So fxy equals fyx, identity, fxz, identity fzx, and fyz equals fzy. No, this does not require a new proof, because if, say, we consider this derivative fxy and fyx, we can forget about the third variable z. It is anyway, it is constant when you differentiate. So we are reduced to the two-dimensional case. So we have the same theorem of equality of mixed second derivatives as in 2 dimensions. So this means that we have not 9 but just 6 independent second derivatives. All other 3 are equal to one of the previous. That's it. So we will extensively use this Clairaut theorem in what follows. Let us finish this small chapter, and soon we will move further. For now, have a good time. Bye.